Um, Hello everyone. Welcome back to the stream, and thank you for joining me live today. Let me start sharing my screen, and then let's get started. Okay. Um, so just in a couple of seconds, we're going to start. So my name is Ilgar Zarbaliev, and in this session, we are getting started with data warehouses in Fabric. If you are watching the replay, please drop a comment with where you are watching from. And if you are here live, say hello in the chat so I know you are with me. Here is the plan for today. This session is the theory part. We will cover data warehouse fundamentals, dimensional modeling, what makes the Fabric warehouse different, and how you query and transform data with T-SQL, how you model it for reporting, and how you secure and monitor it. In the next session, I will take everything we discussed today into the Fabric portal, and we will build it together in a hands-on lab. So today is the map. The next session is the journey. Let's begin. Okay. Actually, here I gave all the necessary information. So a little bit more information about myself. I'm based in Baku, Azerbaijan, and I'm a Microsoft MVP in two categories: data platform and Power BI and M365 Excel. I'm also a Microsoft certified trainer, the MCT community lead, and Microsoft certified educator, Microsoft Innovate educator expert, and the Microsoft Fabric super user. Day to day, I work as a senior manager at some product, an Excel and Power BI consultancy, where I build and deliver training. Alongside that, I lead the Azerbaijan data and AI community, where we run meetups, study groups, and national Excel competitions. This stream is part of my uh, everything is free, everything is recorded, and the aim is simple, just to help you build real job-ready data skills. Right, that's enough about me. Let's talk about where we left off. Quick recap before we move forward, because today builds directly on the last session. In the previous session, we covered the medallion architecture in Fabric. If you just missed it, the say link is in the description, and I would recommend watching it first because everything today sits on top of that foundation. By the way, you can subscribe to my YouTube channel where you can find all these kinds of videos. To remind you, medallion architecture is a way of organizing your data into three progressive quality layers. Bronze is the raw landing zone. Data arrives exactly as it left the source system. We do not clean it. We do not drop anything. We keep the full history so we can always replay it. Silver is the cleansed and confirmed layer. Here we validate, duplicate, apply appropriate data types, and join records into meaningful business entities. Gold is the business ready layer, curated, aggregated, and modeled data shaped specifically for reporting, semantic models, and AI experiences. Here is where we're going today, 6 blocks. First, data warehouse fundamentals, what a warehouse actually is and the dimensional modeling vocabulary unit, fact tables, dimension tables, surrogate and alternate keys, star and snowflake schemas. Second, the Fabric data warehouse specifically, full transactional T-SQL running over data format in OneLake, and the difference between a warehouse and a SQL analytics endpoint, which is one of the most common points of confusion for people new to Fabric. Third, creating a warehouse and getting data into it. Copy into, open row set, pipelines and data flows, cross-database queries, the staging table pattern, and zero copy table clones. Fourth, querying and transforming. The SQL query editor and visual query editor for the no-code approach, and saving your logic as views and stored procedures. Fifth, modeling the warehouse for downstream consumption, relationships, measures, semantic models, and direct lake merge. And six, security and monitoring, the layers of access control and the tools that tell you what your queries are actually doing. Keep your questions coming in the chat as we go. I will pause and answer them along the way. Let's start with the definition because it matters. A data warehouse is a centralized, structured store designed for analytical queries and reporting. The key phrase that is designed for analytical queries. It consolidates data from multiple source systems into a format that is optimized for analysis, not for running the business minute by minute. That distinction is the whole reason warehouses exist. So let me make it concrete. On the left, you have your operational database. This is the system that runs the business day to day. Your point of sale, your ERP, your CRM. It handles a very large number of small reads and writes. It's normalized, which means data is split across many tables to avoid duplication. It's optimized for transaction speed, and it generally holds the current state of things. What's the stock level right now? What's the customer's current address? On the right, you have the analytical warehouse. This one doesn't run the business. It answers questions about the business. It handles large reads and bulk loads instead of thousands of tiny writes. It's deliberately denormalized, which means we accept some duplication in exchange for fewer joins and faster queries. It's optimized for query performance across large volumes. And crucially, it holds history. Not just what the customer's address is today, but what it was when they placed each other. If you have ever tried to run a heavy analytical report directly against a production transactional system, you already know why we separate the two. You slow down the business, and you still get slow reports. Relational data warehouses sit at the center of most enterprise BI solutions for exactly this reason. Whatever technology we use, building a modern data warehouse involves four stages. This is the mental model I want you to carry through the whole session. Stage one, data ingestion. Moving data from your source systems into the warehouses, files, databases, APIs, streams, whatever your sources are. Stage two, data storage. Storing that data in a format that is optimized for analytics. In Fabric, that format is Delta, and the location is OneLake. Stage 3, data processing. Transforming the raw data into a shape that analytical tools can consume. This is where cleaning, joining, and the business rules happen. Stage 4, data analysis and delivery. Actually analyzing the data to produce insight and getting that insight in front of the people who make decisions. Now, here is why I like Fabric for this. Traditionally, each of those four stages was a different product, often from a different vendor, with data being copied at every boundary. Copy from source to staging, copy from staging to warehousing, copy from warehouse to the BI tools or memory. Every copy costs money, adds latency, and creates a chance for the numbers to disagree. In Fabric, all four stages happen on one platform, over one copy of the data in just one lake. That's the single biggest architectural idea in the whole product. And it's why the warehouse integrates so cleanly with everything else. Now the vocabulary. If you take one thing from the fundamentals part of this session, take this slide. We organize warehouse tables to support efficient analysis of very large volumes of data. Um, so that organization is called dimensional modeling, and it splits your tables into two families: fact tables and dimensional just tables, right? So just a minute, please. Okay. Fact tables contain the numerical data that you want to analyze. They are the numbers: sales amount, quantity, cost, duration. Fact tables typically have a very large number of rows, and they keep growing because every transaction adds another row. And they keep growing because every transaction adds another row. They are the primary source of data for analysis, and they hold foreign keys pointing out to every dimension. A classic example: a fact table containing the total amount paid for sales orders that occurred on a specific date at a particular store. Dimension tables contain descriptive information about the data in the fact tables. They are the context: who, what, where, when. And dimension tables typically have far fewer rows, and they give you the attributes that you slice and group by. A dimension table might contain information about the customers: who placed those sales orders, their name, their region, and their segment. Here's the simplest way I explain this to my students. The fact table answers how much. The dimension tables answer by what. How much revenue by customer, by product, by month, by store. Every question a business person asks you is really that sentence in discuss. Every dimension table also carries a unique key column that identifies each row. And that key is the subject of the next slide. Because there is a subtlety there that trips a lot of people up. Okay. The slide answers a question I get in almost every training session. What does my dimension table have two keys? Why not just use the customer ID from the source system? Let's take them at one at a time. A surrogate key is a unique identifier for each row in the dimension table. It's usually an integer that the database management system generates automatically when you insert any row. The important thing is that it belongs to the warehouse. No source systems knows about it. It exists purely to keep the warehouse internally consistent and accurate. An alternate key is often a natural or business key that identifies a specific instance of an entity in the transactional source system. A product code, a customer ID, a SKU, stock keeping unit. So this is the value the business actually recognizes. And it's what allows you to trace a row in the warehouse back to the record it came from. So why both? Three practical reasons. First, you may load from more than one source system, and two systems can easily use the same customer ID for different customers. The surrogate key gives you one unambiguous identity. Second, source systems change. A company migrates from one CRM to another, and every business key is reissued. If your fact tables were keyed on the business key, you would have to rewrite history. If they are keyed on the surrogate key, you just map the new business key in. And third, slowly changing dimensions, which we will see on the next slide, need multiple rows for the same business entity over time. You cannot do that if the business key is your unique identifier, because it would no longer be unique. The summary line at the bottom is the one to remember. Surrogate keys keep the warehouse internally consistent. Alternate keys keep it connected to reality. You need both because they serve different purposes. Two special dimension types deserve their own slide because they provide additional context and unlock a lot of analysis you cannot do otherwise. First, time dimensions. A time dimension provides information about the time period in which an event occurred. And it enables data analysts to aggregate data over temporal intervals. Typically, it includes columns for year, quarter, month, and day of a sales order. Why not just use the date column on the fact table? Because a date column gives you a date. A time dimension gives you a calendar. Fiscal quarters that do not start in January. Public holidays that differ by country. Week numbers, working days versus weekends. Once you have those as columns, your analysts stop writing date arithmetic in every single query. And everyone's fiscal quarter finally means the same thing. One practical tip, you generate the date dimension in advance. One row per date, usually covering a range well beyond today. Second, slowly changing dimensions. These track changes to dimension attributes over time, like changes to a customer's address or a product's price. They're significant in a warehouse because they enable you to analyze and understand changes to data over time. And they ensure the data stays up to date and accurate, which matters for making good business decisions. Here is why this is not academic. Imagine a customer who was in the North region in 2023 and moved to the South region this year. If you simply overwrite the region, then all of the customers' 2023 sales suddenly report under South. Your historical numbers change retroactively, and your finance team will not. A slowly changing dimension preserves the value that applied at the time the fact occurred. So a sale from 2023 still reports against the 2023 region. This is exactly why we need those surrogate keys we discussed a moment ago. The same customer can have several roles, one per version, each with its own surrogate key, but all sharing the same alternate key. Now let's put those tables into a shape. This is the star schema, and it's the default answer for analytics. Start with the contrast. In most transactional databases used in business applications, the data is normalized to reduce duplication. That's correct design for an application. In a data warehouse, however, the dimension data is deliberately denormalized to reduce the number of joins required to query the data. We accept some duplication in exchange for speed and simplicity. What you see here is the result. The fact table sits in the center, and each dimension table relates directly to it. Draw the lines, and it looks like a star, which is where the name comes from. The practical benefit is that any attribute in any dimension is exactly one join away from any measure in the fact table. Sales by customer region, one join. Sales by product, category, one join. Sales by fiscal month, one join. So your query stays sharp, your query engine stays happy, and your business users can navigate the model without a diagram in front of them. One more useful property. You can use dimension attributes to group fact table numbers at different levels. You could find the total sales revenue for a whole region or just for one customer. And you store the information for each of those levels in the same dimension table. Region, country, city, customer, all as columns on team customer. That's the normalization working for you. If you want to go deeper on this, the Power BI guidance article called What's a Star Schema is genuinely one of the best pieces of documentation Microsoft just publishes. I will drop the link in the chat. The snowflake schema is the variation you reach for when a pure star starts to feel wasteful. Here is what has happened in this diagram. The dim product table has been split or normalized into separate dimension tables for product categories and suppliers. Each row in dim product now contains key values for the corresponding rows in dim category and dim supplier. On the right, a dim geography table, this one, um, contains information on where customers and stores are located. Dim store and dim customer. Each row in dim customer here and each row in dim store contains a key value pointing to the corresponding row in dim geography. That's the shared attribute case. Rather than repeating the same city, country, and region columns in two separate dimensions, you hold them once. Draw the lines here and it no longer looks like a star. It branches out, which is where the snowflake name comes from. So, when do you choose this? The honest answer is less often than you might think. Snowflaking makes sense when you have many levels or attributes genuinely shared by different entities, or when a dimension is so large that repeating the descriptive columns is materially expensive. The cost is that every additional level is another join at query time, and the model becomes harder for business users to read. My general guidance to TMCs start with a star and only snowflake where you have a concrete reason. Do not snowflake because it feels tedious, because tediness in a warehouse is not the goal. Query performance and clarity for consumers are the just goals. Right. That's the theory of dimensional modeling. Let's now bring it into Fabric. This is our foundation. Facts, dimensions, keys, star, snowflake. Those concepts are decades old and they apply to any warehouse technology you will ever touch. Now let's see what Microsoft Fabric adds on top of them. Because this is where it gets interesting. And this is where Fabric differs from a traditional warehouse. If you have questions on the modeling part, now it is a good moment to put them in the chat and I will pick them up just, shortly. Okay, good. So what exactly is a Fabric data warehouse? The formal definition is saying that it's a fully managed enterprise scale relational database built on OneLake. And it provides full transactional T-SQL capabilities with full ACID compliance for data consistency. Let me unpack the three things on this slide because each one is doing real work. First, DDL statements: create, alter, draw. You define and evolve your schema using the same T-SQL syntax you would use in SQL Server. If you have written SQL Server DDL, you already know how to do this. There is nothing new to learn. Second, DML statements: insert, update, delete, and importantly, merge. I want to pause on this because if you have worked with big data platforms, you will know that update and delete were historically painful or simply unavailable. You appended and you rewrote entire partitions. Here, you get genuine transactional rights with a seat guarantees, and merge gives you proper just absurd behavior in a single just statement, which is exactly what you want for loading slowly changing dimensions. Third, and this is the architectural piece, data is stored in open data format on OneLake. That means other Fabric workloads can access the same data without duplication. Your Spark notebooks, your lakehouses, your Power BI semantic models, your data agents all reading the same files, not a copy, the same files. Put those together and you get something quite unusual. The familiarity and transactional strengths of a relational database on top of open lake storage with no data movement between just workloads. Six capabilities that define the Fabric warehouse. I will go through them quickly, but each one removes a real problem that used to cost teams time. One, full T-SQL support, DDL and DML, including merge for absurd scenarios using familiar SQL Server syntax. Your existing SQL skills transfer directly. Two, fully managed. There is no infrastructure to configure, no nodes to size, no distribution keys to choose, no service to pause. And resume. Compute scales automatically and independently from storage. If you have ever-sized a dedicated SQL pool, you will appreciate what has been taken away here. 3. OneLake integration. Warehouse data is stored in Delta format and is accessible by other Fabric workloads without duplication. One copy, many engines. 4. Cross database querying. You can query across warehouses and lakehouses without copying data using three-part naming: database, schema, table. That means you can join a warehouse table to a lakehouse table in a single query. In practice, this is enormous. It means you no longer have to decide in advance whether something belongs in the lakehouse or the warehouse in order to use them together. 5. Familiar tooling. Connect with SQL Server Management Studio, Azure Data Studio, or any SQL client through standard TDS connections. Your team keeps the tools it already knows. And 6, Copilot assistance. Copilot for data warehouse generates SQL queries from natural language, provide code compilation as you type, and can explain or fix existing queries directly in the SQL editor. I will show this live in the lab session because it's genuinely useful, particularly for people who know their data well but write SQL only occasionally. This is the slide I would screenshot if I were you, because this single distinction causes more confusion than anything else in Fabric. The Fabric workspace can contain two types of SQL-based item, and in the portal, they both give you a SQL editor that looks and feels the same, right? But they serve different purposes. Look at the table. Both can read data, both can create views and stored procedures. That's where the similarity ends. Only the warehouse can write data, insert, update, delete, merge. The SQL analytics endpoint just cannot. Only the warehouse can create tables with DDL. The SQL analytics endpoint can't. And the data source is different. A warehouse holds native warehouse tables that it owns. A SQL analytics endpoint sits over data tables that belong to a lakehouse. The endpoint is a read-only SQL window onto data that something else, usually Spark, is writing. So here is the second rule. Use a warehouse when you need full read and write T-SQL capabilities. Use the SQL Analytics endpoint when you need read-only SQL access to lakehouse data. If you have ever opened a SQL editor in Fabric, written a perfectly valid insert statement, and received an error telling you the operation is not supported, this table is your explanation. You were on the endpoint, not on a warehouse. And remember, the medallion recap from the last session. A very common pattern is Spark writing bronze and silver in the lakehouse, and the warehouse serving the gold layer with full T-SQL. The two are complements, not competitors. Creating the warehouse itself is almost anticlimactic, and that's the point. You cannot create a data warehouse in Fabric from the Create Hub or from within a workspace. Both routes give you the same item, so use whichever fits your workflow. You then get an empty warehouse. From there, you add tables, views, stored procedures, and other objects. And once your warehouse exists, you can start creating tables and loading data using the SQL query editor right in the Fabric portal. No client tool needed to get going, although you can absolutely connect SSMS or Azure Data Studio if you prefer. I want you to note what's not on this slide. There is no step where you choose a service tier, no step where you size compute nodes, no step where you pick up a distribution strategy for each table, no step where you configure storage separately. If you have provisioned a traditional MPP warehouse, you know that those decisions used to come first. They were hard to reverse, and getting them wrong was expensive. Here, you name it and it exists. Compute scales automatically and independently from storage. We will do this live in the next session. So if this feels abstract right now, that's fine. Today, the goal is that you understand what you are about to click. You have a warehouse and now you need data in it. There are four main routes, and choosing the right one saves you a lot of work. Copy into is your bulk loader. It loads data from external files, typically CSV or Parquet, sitting in Azure storage, straight into warehouse tables. If you have a nightly drop of files, this is your command. Open row set lets you query files directly from external storage or OneLake locations for ad hoc analysis or ingestion without creating tables first. This is excellent for exploration. Someone sends you a file and you want to see what is in it before you commit to a schema. Point, open row set at it and look. Pipelines and data flows are the orchestration route. Data factory pipelines and data flows Gen 2 give you scheduled low-code data movement and transformation with connectors to hundreds of sources. This is where most production ingestion ends up living. And the fourth one is my favorite because it's the one people forget. Cross database queries. You can query lakehouse tables directly from the warehouse using three-part naming without copying data at all. Let me stress that last point because there is a tip about it in the documentation and it's worth repeating. If you have tables in a lakehouse that you want to query from your warehouse without making changes to them, use cross database querying instead of copying. You do not need to copy the data. Every copy you avoid is storage you do not pay for. Latency you do not introduce, and the reconciliation problem you never have to debug. So, before you write an ingestion pipeline, always ask yourself, do I actually need this data to move? Or do I just need to read it? Here is copy into in practice. I want to walk through it line by line because the syntax is simple, but each part matters. Line 1, copy into dbo.region, right? This is the destination table in the warehouse. It has to exist all of this. So your create table runs first. Line 2, from, followed by the URL of the source file in Azure Blob Storage. You can also point at a folder or use wildcards to pick up many files in one statement. Then the with block, which holds the options. File type tells the command what it's reading. In our case, it's CSV. It can be either CSV or Parquet. My advice, prefer Parquet where you have the choice. It's columnar, it's compressed, it loads faster, and it carries its own schema. So you avoid a whole category of type guessing problems. Credential is how the warehouse authenticates to the storage account. In this example, a shared access signature. In production, you would prefer managed identity or workspace identity rather than a secret embedded in a script. And you would never commit a real secret to source control. First row equals to skips, the header row of the CSV. A small option that causes a surprising number of failed loads when people forget it, because your header text ends up being inserted as a data row and the type conversion fails. And then go to run the batch, this one. One more time, the tip at the bottom. If the data already sits in a lakehouse and you do not need to change it, use cross database querying instead. Do not copy what you can simply just read. Okay. Now we create the tables. And here you can see the theory from the first half turning into actual code. Look at the customer on the left. Customer key is the surrogate key, an integer, this one. Customer alt key is the alternate key, the business identifier from the source system. Then customer name and region, which are the descriptive attributes we slice by. Exactly the structure we discussed on the key slide. Then fact tables. Notes what it contains and what it does not. Sales key identifies the row. Customer key, product key, and date key are foreign keys out to the dimensions. Sales amount and quantity are the measures. There is no customer name here, no product description, no month name. All of that context lives in the dimensions. No month name, actually in the dimensions. That spleen is what keeps the fact table narrow. And a narrow fact table is a fast fact table when it has hundreds of millions of rows. On the right, data type guidance, because the choice you make here follow you forever. The int for key columns, they're compact. They join quickly, and they are ideal for surrogate keys. Varchar. Use varchar for text that may include special characters. This matters a great deal if you work with no Latin alphabets, and in my region, it's not optional. Decimal. Use decimal for financial values that require precision. And please never use float for money. Floating point arithmetic will give you totals that are off by fractions of a currency unit. And you will spend an afternoon explaining to finance why the report and the ledger disagree by 3 cents. So the general principle is to balance precision with storage efficiency. Do not define every text column as mvarchar max because you cannot be bothered to check the real length. This is one of the most important practical patterns in the whole session. So let me spend a moment on it. The pattern is land raw data in staging tables first, then transform and load it into your final dimension and fact tables. Staging tables mirror the structure of your source data and act as a temporary holding data. Look at the flow at the top. Source files come in through copy into or a pipeline and land in staging tables. Staging tables look like the source, not like your model. Then a second step transforms that staged data into a dimensional model. Now look at the SQL, this part. Because this is where the surrogate key story finally just pays off. We insert into fact tables, sales, right? Selecting from the staging table stage sales from here. But notice the joins. We join staging to dim customer. S dot customer ID equals C dot customer alt key. So here. We join, the source system gave us a business key. We join on that business key to find the matching dimension row. And then we take that row's surrogate key, customer key, into the fact table. The same thing happens for product and for date. That operation has a name in warehousing. It's called a key lookup, and it's what converts source systems identifiers into warehouse internal identifiers. Why not load straight from file into the fact table and skip staging? 3 reasons. One, your source data almost never matches your model shape, and you need somewhere to do that work. Two, if a load fails halfway, you still have the stage data and you can rerun the transformation without going back to the source. And three, this is where you apply business rules and data quality checks in a place where you can inspect the before and after. The pattern keeps your source data intact while you apply business rules and key lookups during the load. Simple, and it will save you a lot of pain. Here is a capability that does not exist in traditional warehouses, and once you have it, you will use it constantly. You can create zero copy table clones in a Fabric data warehouse. A clone copies the table metadata while still referencing the same underlying data files in OneLake. The data itself is not duplicated, which keeps storage costs low. The syntax is one line. Create table dbo.employee as clone of dbo.employee USA. This one. That's it. It completes almost instantly regardless of table size. Because nothing is being copied, you are creating a new pointer to the same data files. Three places where this earns its keep. First, development and testing. You can give every developer on your team a full-size copy of production data to work against without paying for a full-size copy. When they break it, they drop it and clone it. Compare that to the traditional approach of restoring a backup for hours or working against a sampled subset that does not reproduce the bugs you actually have. Second, data recovery. After a failed release, clone your tables before you deploy. If your release goes wrong, you have an instant restore point and you did not have to schedule a maintenance window to take a backup. Third, preserving data at specific points in time for historical reporting. Month-end snapshots for audit, for example. One thing to be aware of, and I will show this in the lab. A clone is a snapshot, right? Clone is a snapshot at the moment of creation. It does not stay in sync with the source table afterwards. Changes to the source do not appear in the clone, and changes to the clone do not affect the source. That independence is exactly what you want for testing, but do not mistake a clone for a live replica. We have a warehouse, we have tables, we have data in them. Now we flip it. Raw data rarely arrives in the exact format you need for analysis. You might need to join tables, filter rows, aggregate values, or restructure things before any of it is useful for just reporting. In this part, we look at the two query experiences Fabric just gives you. How to save your transformation logic so you are not rewriting it every time. And then how to model the warehouse so that Power BI, Copilot, and your analysts all get consistent answers. Fabric gives you two tools for scraping data, and I want to be clear that neither one is the beginner option. They save different people and different moments. On the left, the SQL query editor. It provides a query experience with intelligence, code completion, syntax highlighting, and client-side parsing and validation. If you have written T-SQL in SQL Server Management Studio or Azure Data Studio, this will feel immediately familiar. You create a new query with the new SQL query button. And Copilot for data warehouse lives right here in the editor. It generates queries from natural language, completes code as you type, and can explain or fix existing queries. That last one is underrated. Inheriting a 200-line query someone wrote 3 years ago and asking Copilot to explain it's a genuinely good use of your time. On the right, the visual query editor. It provides an experience similar to the Power Query online diagram view, which many of you will already know from Power BI and from data flows. You create one with the new visual query button. Drag a table from your data warehouse onto the canvas, and then use the transform menu at top to add columns, filters, and other transformations. You can also use the plus button on the visual itself to do the same things. This is a serious tool, not a toy. For analysts who know their data extremely well, but write SQL only occasionally, the visual editor removes the syntax barrier without removing the capability. My practical advice for teams, let people use whichever one gets them to the answer. Then, when a query becomes something the business relies on, promote it into a view or a stored procedure, which is exactly where we are going to going next. Beyond ad hoc queries, you can just save your transformation logic as reusable objects in the warehouse. There are two of them, and they do different jobs. Views define a saved query that you reference like a table. Use views to standardize how analysts access data. For example, combining fact and dimensional tables into a reporting friendly format or filtering rows down to a specific business context. Stored procedures contain T-SQL logic that you execute on demand. Use them for repeatable transformation tasks, like loading staging data into final tables or applying business rules. Remember, the staging insert we looked at a few slides ago, that belongs in a stored procedure, not pasted into a query window every night. Look at the example on the right. It creates a view called with W underscore sales by region. It joins the fact table to the customer dimension, groups by region, and returns total sales and order count. Now, think about what that one object prevents. Without it, five different analysts write five different versions of regional sales. One of them forgets to exclude canceled orders. Another joins on the wrong key. And then you have a meeting where three reports disagree and nobody can say which is right. With the view, there is one definition and everyone shares it. And there is a modern reason to care about this too. In the box at the bottom here, uh, views and stored procedures also make your data more accessible to AI-powered tools. Copilot and Fabric IQ data agents can query views just like tables. So standardizing your data access through well-named views directly improves the accuracy of natural language just queries. Think about that for a moment. If you called with W underscore sales by region, this one, with clear column, names like total sales, gives an AI agent a much better chance of answering what were our sales by region last quarter correctly than a pile of row tables with abbreviated column names. Good modeling has always helped humans. Now it also helps the machine. Now we move into modeling, and the first step is not relationships. It's cleaning up what consumers actually see. Here is the problem. Without data modeling, every consumer has to work out which tables relate to each other, write their own aggregation logic, and guess at what the columns mean. Data modeling solves that by embedding structure, business logic, and documentation directly into the warehouse. And raw warehouse tables are messy from a consumer's point of view. They contain staging tables, surrogate key columns, and internal flags that exist for ETL processing, not for analysis. All of that creates noise when someone browses the data. So in the model view, three practical steps. Hide internal objects, staging tables, surrogate key columns, ETL artifacts. Nobody building a report needs to see stage sales or customer key. Hiding them is not about secrecy. It's about reducing the choices a consumer has to filter through. Then rename columns to business-friendly names where the warehouse names are technical or abbreviated. The example in the documentation is perfect. Rename cost region to customer region, right? Your ETL developer knows what cost region means. Your finance manager does not and should not have to. Then add descriptions to tables and columns. So consumers understand what the data represents without having to find external documentation. Be honest with yourself here. That documentation you promised to write in Confluence, did it get written? Description live with the data and travel with it. And read the dark box at the bottom, this one. Because this is the part that has changed recently. Three steps matter beyond tidiness. Copilot in Power BI and Fabric IQ, data agents rely on table names, column names, and descriptions to interpret natural language questions and generate accurate SQL or DAX. A column named customer region with a description saying it's the geographic region of the customer's primary address produces better natural language results than cast RGN with no description at all. Your metadata is now part of how the AI understands your business. Sloppy naming used to cost you a support question. Now it costs you a wrong answer delivered confidently. With clean, well-named tables in place, we define how those tables connect. A relationship is a logical connection between two tables that enables filtering, grouping, and aggregation across those tables. In a star schema, relationships connect fact tables to dimension tables through shared key columns. Concretely, the customer key column exists in both fact sales and team customer. That shared column establishes the link that lets you analyze sales by customer attributes like region, segment, or account type. Every relationship has two properties you need to understand. Cardinality describes how rows in the two tables correspond. In a star schema, fact-to-dimension relationships are typically many to one. Many fact rows map to a single dimension row. Thousands, thousands of orders, one customer. That's the normal health shape. Cross-filter direction determines which way filters propagate between the tables. Single direction, where the dimension filters the fact table, is the standard setting for most star schema designs because it keeps filter behavior predictable and performant. If you have ever set a relationship to both directions in Power BI and then spent an afternoon working out with the total was wrong, you know why single is the default advice. And why bother at all? Look at the dark box. Without defined relationships, every consumer who wants to combine data across tables needs to write explicit join logic correctly every single time. And relationships eliminate that repetition by encoding the connection once. And again, the AI angle, when you create a semantic model from the warehouse, these relationships inform how Power BI, Copilot, and Fabric IQ data agents interpret the data. Data agents use relationships to generate accurate joins when translating natural language questions into SQL. If the relationships are missing or wrong, the agent guesses, and the confident wrong answer is worse than no answer. Most data warehouses use dimensional modeling for exactly this reason. Relationships shape the star schema, and the star schema is the ideal model for analytics. Tables are clean, relationships are defined. The next step is giving consumers reliable, consistent ways to query and calculate. The problem we are solving is stated in the line at the top. Without standardization, each team writes its own join logic, applies its own filters, and defines its own formulas, which leads to conflicting results. Every one of you who has sat in the meeting where two departments presented different revenue numbers knows exactly what this costs. Two tools covering the two sides of consumption. Views provide consistency for T-SQL consumers. A view encapsulates join logic, filters, and column selections into a reusable query that consumers reference like a table. For example, a view that joins fact and dimension tables, filters to complete orders, and surfaces only the columns analysts need, gives every T-SQL consumer a reliable starting just point. Views also serve as stable data sources for reports. Rather than building reports directly against base tables that might change, you point reports at views that present a consistent shape. Then, when you refactor the underlying table, you update the view and the reports keep working. That's a genuine architectural benefit, not just tidiness. Measures provide the same consistency for DAX calculations. A measure is a reusable DAX expression that defines a calculation like a total, average, ratio, or count. You create measures directly in the warehouse model view by selecting a table and adding a new measure. The total sales measure that sums sales amount ensures every consumer uses the same calculation. And because the measure definition lives with data, it becomes the single source of truth for that metric. When the business changes how it calculates revenue and it will, you update the measure in one place rather than tracking down every report that contains its own version of the formula. Together, they cover both sides. Views standardize how T-SQL consumers access and query data. Measures standardize how business calculations appear in reports and dashboards. Text formulas and advanced measure design are a topic in their own right, and we will cover them properly in a later session. Okay, last piece of the modeling story, and it connects back to the very first architectural idea we discussed. With prepared tables, defined relationships, and standardized views and measures in place, the warehouse is ready for downstream reporting. Teams that query the warehouse directly using T-SQL or connect through third-party tools can work with the warehouse model as it is. But when you want interactive Power BI reports and dashboards, you create a semantic model. Now, semantic models created from a fabric warehouse use direct lake mode. And this is worth understanding properly because it changes how you think about fresh. On the left, import mode, the traditional approach. It copies data into Power BI memory. That copy has to be refreshed on a schedule. So your reports show data as of the last refresh, not as of now. And you are maintaining and paying for a second copy of data you already have. On the right, direct lake mode. Instead of copying, it reads data directly from the OneLake Parquet files. That means reporting reflects the latest warehouse data without requiring scheduled refreshes. And you avoid the storage and processing overhead of maintaining a separate copy. Think about what disappears here. The refresh window that fails at 3 in the morning. The gap between the data being loaded and the report showing it. The conversation where someone says the dashboard is wrong and you have to explain it's just 8 hours old. This is the one lake principle again, and it's the thread running through the entire session. One copy of the data, read by every engine that needs it. Semantic model design and scalability patterns are a big topic in their own right, and there are dedicated models on that. Today, I want you to live knowing that direct lake exists, that it's the default for warehouse and semantic models, and why that matters. Security and monitoring are critical to managing a warehouse. And Fabric gives you multiple layers of protection. The design goal here is worth stating explicitly. Security operates at multiple levels, from workspace access all the way down to individual rows and columns. That design lets you support the distinct needs of your organization while still allowing the democratization of data. In other words, you can give people access without giving them everything. Layer 1, workspace roles. Data in Fabric is organized into workspaces, and workspace roles are your first layer of access control. You assign users to roles based on the level of access they need. Admins have full control. Viewers can view items but cannot make changes. Most access problems people bring to me are solved at this layer, usually by discovering that someone was made an admin when they should have been a viewer. Layer 2, item permissions. In addition to workspace roles, you can grant item permissions to share an individual warehouse without granting access to the entire workspace. This granularity is useful when you need to share one warehouse with specific users for downstream just consumption. There are three to know. Read allows the user to connect using the SQL analytics point. Read data allows the user to read data from any table or view in the warehouse. Read all allows the user to read the raw Parquet files in OneLake. And note the box at the bottom. Because this one generates support tickets. A user connection to the SQL analytics endpoint fails without a read permission at a minimum. If someone tells you they cannot even connect, start there. Layer 3 is granular SQL security and it deserves its own slide, so let's turn to it. Four granular security features, all defined in T-SQL, all restricting data visibility without changing the underlying tables. Object-level security controls access to specific tables, views, or procedures. The straightforward one. This user can see this view, not that table. Row-level security restricts which rows a user can see, using where clause predicts. This is how you give every regional manager the same report and have each of them see only their own region. One report, one dataset, filtered per user by the engine. Column level security restricts which columns are visible to specific users. The salary column exists, the analyst can query that table, but that column is not returned to them. Dynamic data masking masks sensitive data, such as email addresses or account numbers, from non-privileged users. The data is still there, but a non-privileged user sees a masked value. Useful for support teams who need to confirm the last four digits without seeing the whole number. Now the sentence at the bottom is the one I want you to remember. And it's the reason all of this belongs to the database rather than in the report. Securing your warehouse data matters for regulatory compliance and for ensuring that AI powered tools like Copilot and data agents operate within governed boundaries. Security policies you define in T-SQL are enforced regardless of how the data is accessed. Think about what that protects you from. If your security lived only in the Power BI report, then the moment someone connects with SSMS or asks a Copilot agent a question, your controls are gone. Because these policies live in the warehouse, the agent is subject to exactly the same restrictions as the human. It cannot reveal what the user is not allowed to see. That's a very reassuring property when you are being asked to roll out AI over sensitive data. And it's one of the strongest arguments for putting our data in a warehouse in the first place. So row level, column level, and dynamic data masking each to go deeper than we can go today. And there is a dedicated model on securing a fabric warehouse if you want the detail. Last technical topic, monitoring. Pardon. Because a warehouse that nobody wants will eventually surprise you. Monitoring warehouse activity helps you identify performance issues, optimize queries, and understand usage just patterns. Two tools. Query Insights provides a central location for historical query data and actionable performance information. It retains data for 30 days and it helps you identify long running queries, track how performance changes over time, and understand which queries consume the most resources. It works through system views. You can query directly with T-SQL and reverse knowing here. The first one is exec underscore requests. This one, exec underscore requests. History. Actually, I don't see history here. So underscore history we can add. So exec underscore request underscore history returns information about each completed SQL request. Long running queries, between them there is underscore, returns queries ranked by execution time. And exec underscore sessions underscore history returns information about completed sessions. That first one, long underscore running underscore queries, is where this one, we're talking about this one, is where I would start on any warehouse I inherit. Sort by execution time, and you will usually find that a small number of queries account for most of your consumption. Fix those and everything gets better. The second tool is dynamic management views or DMVs. These monitor active connections, sessions, and requests in real time. The example on screen uses sis.dm underscore exec underscore requests. It's just for identifying currently running queries. Filter to status running, ordered by, say, elapsed time descending. This is your what is happening right now and what is holding everything up query. Two permission nodes. You must be a workspace admin to run the kill command and terminate a long-running session. And members, contributors, and viewers can see their own results but cannot see other users' queries. So if you are troubleshooting on behalf of someone else and the DMV looks empty, check your roles. So yeah. Okay. Actually, yeah, we have talked about this. So now let's pull it together. 6 things I want you to live with. 1, facts and dimensions. Numbers go in fact tables, right? Context goes in dimension tables. That single split drives every other modeling decision you make. Two keys, two jobs. Segregate keys keep the warehouse internally consistent. Alternate keys keep it traceable back to the source system. You need both, and now you know why. 3, start first. Start with a star schema because it gives you one join between any attribute and any measure. Only snowflake when you have a concrete specific reason, not because it feels tidier. 4, warehouse means right. A fabric warehouse gives you full transactional T-SQL, including merge, with ACID guarantees. The SQL analytics endpoint is read-only over lakehouse data. If you remember one table from today, make it that comparison. 5. Do not copy what you can read. Cross database queries, zero copy clones, and direct lake all rest on the same idea. One copy of the data in OneLake. Read by every engine. Every copy you avoid is cost. Latency and reconciliation pain you avoid. And 6, the one that has changed most recently. Metadata is now functional, not decorative. Your table names, your column names, your descriptions, your views, and your relationships are just what Copilot and Fabric IQ data agents read in order to answer questions. Good modeling used to make life easier for people. Now it also determines whether the AI gives your business a right answer or a confident wrong one. If those 6 land, today has done its job. And that brings us to the end of this theory. Here is what happens next. In the next session, I will demonstrate the lab. Everything we have discussed today, we will build together live in Microsoft Fabric with my screen shared step by step. We will create a warehouse from the Create Hub in a real workspace. We will load data using copy info, land it in staging tables, and run the key lookups that turn business keys into surrogate keys, exactly as we saw in the code today. We will query it in both editors, the SQL and the visual one. We will use Copilot write some SQL for us, and we will save our logic into views and stored procedures. Then we will model it. Define relationships, add a measure, create a direct lake semantic model, apply row-level security, and finish by looking at query insights. See what our own queries actually cost. So today was the map. Next time is the journey. If you want to follow along live, get a Fabric trial set up before then, and I will post a prerequisite in the description so you arrive ready. Before you go, 3 quick asks. Please like the video. It generally helps other people find this series. Subscribe and turn on notifications so you do not miss the lab session. And leave your questions in the comments. I read everyone and I often turn the good ones into their own session. Thank you very much for watching. See you in upcoming session.